Dear students, in the last sessions we saw Wilson's theorem and Fermat's theorem. Fermat's theorem says that if p doesn't divide a, then a to the power p minus 1 is congruent to 1 modulo p. Now consider this following discussion. There are 4 positive integers less than or equal to 12 and relatively prime to 12, right? They are namely these 4 numbers. If you take 1, that is less than 12 and relatively prime to 12, and 2, if you take 2, that is not relatively prime to 12, 3 is not relatively prime to 12, and 4 is not relatively prime to 12, but 5, which is less than or equal to 12 and relatively prime to 12. Similarly, 6 is not, 7, 8 is not, and 9 and 12, they are not relatively prime. So these are the only numbers which are less than or equal to 12 and are relatively prime to 12. And see, this is going to satisfy some beautiful conditions. This 1 to the power, there are how many numbers? There are 4 numbers, right? That 4 is this one. 1 to the power 4 is congruent to 1 mod 12. And 5 to the power 4 is congruent to 1 mod 12. 5 power 4 means 5 square into 5 square. But here 24, if 24 goes, it is 1, and here it is 1. So we get 1 mod 12. Similarly, 7 to the power 4 is congruent to 1 mod 12. Check yourself. And 11 to the power 4 is congruent to 1 mod 12. 11 power 4 means 121 into 121, but 120 will go, so 1 into 1. So there are 4 numbers, and that 4 is indicated here, and any number power that 4 is congruent to 1 mod 12. This is going to be some general theorem than the Fermat's theorem. And that theorem is going to be called Euler's theorem. Before seeing the theorem, Euler's theorem, just let us discuss few things. In the first unit, we have studied this is a group. This is a group. ZP star. What is ZP star? 1, 2, 3, etc. P minus 1. This is a group under the multiplication modulo P, under the operation multiplication modulo P. And by application of Lagrange's theorem, for any element here, if you take any element A here, A to the power order of G is equal to identity. Here what is the order? P minus 1 is the order. And what is the identity? 1 is the identity. So we can write this as 1 modulo P, right? We can write this one. A to the power P minus 1. If we find this modulo P, we will get 1. Right? So we have studied this one in the first unit. See, this is the Fermat's theorem, right? This is the Fermat's theorem. Similar arguments using Lagrange's theorem, we could prove it in one line, right? Similarly, let us see one more concept. UN. What is UN? U of n is equal to set of all positive integers less than or equal to n and relatively prime to n. Okay, so what is U of 10? U of 10 means there will be 1 but not 2, but 3, not 4, but not 5, but not 6, but 7, 8, and there is no 8 but 9. This is U of 10. Okay. In the first unit you have studied U of n with respect to the operation multiplication modulo n is a group. Okay. Operation is modulo n, multiplication modulo n. And in U of 2, how many elements are there? There are only 4 elements. Just now we saw. What are those 4 elements? This is U4, right? 1, 5, 7, 11. There are only 4 elements, 4 numbers. Again, it is a group, right? It's a group with respect to multiplication modulo 12. It's a group. Again, by the application of Lagrange's theorem, here if you take any number a here, a to the power order of g, here what is the order? 4 only. A to the power 4 is equal to 1. A to the power 4 is equal to 1. So this can be written as a power 4 is congruent to 1 modulo m. Here the operation is multiplication modulo 12. It is set now if we consider this as a numbers not in the group, then we get a to the power 4 is congruent to 1 modulo 12. This theorem, this is the general version of this theorem. This kind of results is going to be called Euler's theorem. In this way, one can prove Euler's theorem also using Lagrange's theorem. And before seeing the statement, let us see a few definitions, and then let us see Euler's theorem. Before that, we shall see Euler's phi function. Let m be a positive integer. M is a positive integer. What is phi of m? Then phi of m denotes the number of positive integers less than or equal to m and relatively prime to m. It actually denotes the number. It counts the number. What is u of 1? U of 1 is 1 only. So phi of 1 is equal to 1. What is u of 2? U of 2 means set of all numbers less than or equal to 2 and relatively prime to 2. This is just 1 only. So what is phi of 2? How many positive integers are there which are less than or equal to 2 and relatively prime to 2? Only one number. And what is phi of 6? Phi of 6. What is u of 6? U of 6 means set of all integers, positive integers less than or equal to 6 and relatively prime to 6. This is 1. But not 2. 2 is not relatively prime to 6. Not 3, not 4, but 5. So these are the only two positive integers less than 6 and relatively prime to 6. So there are only 2. So phi of 6 is equal to 2. So this phi denotes the number of positive integers. Number of positive integers that are less than or equal to m, also relatively prime to m. Take 11. 11 is a prime number, right? So if you see any number, any positive integers below 11, all will be relatively prime to 11, right? Because it's a prime number. So any positive integers less than 11 will be relatively prime to 11 only. So what is phi of 11? It is 10 only. Moreover, phi of any prime number p is equal to p minus 1. Phi of any prime number p is equal to p minus 1. Now let us see similarly phi of 18. For 18, these are the only numbers which are less than 18 and relatively prime to 18. Okay. So what is phi of 18 then? Phi of 18 is 1, 2, 3, 4, 5, 6. Phi of 18 is 6. So we have seen what is Euler's phi function. Euler's phi function is denoted in this symbol. How to this is the symbol phi of m. Okay. Now let us see a lemma, a simple lemma. A positive integer p is a prime if and only if phi of p is equal to p minus 1. A simple proof. Let us see what it says. If p is a prime number, this is equal to p minus 1. If for some p, phi of p is equal to p minus 1, then that p also must be a prime number. It is if and only if proof. So let us prove in the first way. Let us now assume let p be a prime number. P is a prime number. Now what we have to prove? We have to prove this one. Let p be a prime number. Then there are p minus 1 positive integers which are less than or equal to p, and all these numbers are relatively prime to p, right? Right? Actually 1, 2, etc. up to p minus 1. All are less than or equal to p and relatively prime to p, right? But see p, the number p, which is also less than or equal to p, but not relatively prime to p. It has common divisor p. So there are p minus 1 numbers which are relatively prime to p and less than or equal to p. So what is phi of p? So p minus 1. Conversely, now we are going to assume this one and we are going to prove that p is a prime. Conversely, let p be a positive integer such that this condition holds. Now take any d which is less than p and greater than 1. Okay? Surely that will not divide p. That will not divide p. Why? Because see, phi of p is equal to p minus 1. Actually phi of p is equal to p minus 1. Below p, 1, 2, 3, 4, etc. p minus 1. There are only, these are surely for the number p. For the number p, p is not relatively prime to p. If p is greater than 1, then p is not relatively prime to p. Okay? So we have, see, these are the numbers which are less than p. Okay? There are p minus 1 numbers. Suppose there is a d in this interval that divides p, then that particular number should be avoided. So then phi of p cannot be p minus 1. There can be at the most p minus 2. So if you take any d between this interval, that will not divide p. So p must be a prime number. P must be a prime number. Okay. Now let us see one more concept and then Fermat's theorem, one lemma and Fermat's theorem. Let m is equal to 12 and a is equal to 35. M and a are relatively prime. M and a are relatively prime. Okay. The least residues modulo 12 that are also relatively prime to 12 are this one. What are these numbers? These are the numbers less than or equal to 12. That means least residues. Least residues means these are the positive integers less than or equal to 12 that are also relatively prime to 12. Okay, these are the numbers. This is actually u of 12 element, the elements of u of 12, right? Now we'll see. What is this one? These are the elements of u of 12. These are the numbers which are relatively prime to 12 and less than or equal to 12. Okay, and also positive integers. See here, 35 is relatively prime to 12. 35, let it be. Okay, I have written 35 here. 35, 35, 35. Here it is mod 12 only. Okay, just I am multiplying with this least residues also relatively prime to 12. I am multiplying with these numbers and I am taking modulus 12. I am getting some reminders. When I take this modulo 12, I get the remainder 11 because 24 will go. 2 12s are 24, so I get the remainder 11. Similarly, here I get the remainder 7. Here I get the remainder 5. When I divide this one by 12, I get the remainder 1. Okay. Here the thing is, these numbers actually 1, 5, 7, 4. I am multiplying 35 by these 4 numbers. Again I am getting 1, 5, 7, 11. But in some different order. We don't know what order it is. But anyway, if we multiply any number that is relatively prime to 12 by these 4 numbers, we will get these 4 numbers again in some order. That is sure. Now let us prove a lemma. Similar lemma. Let us prove similar lemma. Okay. This is actually, here it is called M. Here it is called, it is called A. It is called M. Okay, modulo M. Just now read the lemma. Now let us prove the lemma. Let M be a positive integer and A be any integer with A is relatively prime to M. Let R1, R2, etc. R phi of M be the positive integers less than or equal to M and relatively prime to M. These are the elements of U of M. U of M. In U of M there will be how many elements? There will be phi of M elements. Okay. Let R1, R2, etc. R phi of M be the positive integers less than or equal to M and relatively prime to M. Okay. A be some integer relatively prime to 1. But these are the numbers like 1, 5, 7, 11 for 12. Okay. Then the least residues of the integers. AR1, 35 into 1, 35 into 5, 35 into 7, like here AR1, AR2, etc. A times R phi of M modulo M or a permutation of the integers, this one. If you take modulo M for each integers, for each of these integers, we will get these phi of M integers in some order. This is the statement. Now we have to prove it. So the first thing is, we are going to show that if you take modulo M for any of these numbers, if you take modulo M, we will get a number here. We will get some number here. That I have to prove first. That means if we take modulo M to this number, we will get we won't get 0, or we will get a number here means. So if we take modulo M to this number, we wish to show that we will get a remainder here. That means we wish to show that each of these numbers is relatively prime to M. That one we want to show that one. If see here, if ARI is relatively prime to M, then if you find ARI congruence to some K mod M, surely this K, also assume that this K is least residue modulo M. Okay, this K also will be in this set. Okay, let us see how it is. Suppose ARI is congruent to K mod M, where K is the least residue of modulo M. From this, what we can write? ARI is equal to some L times M plus K, right? Suppose this K is not related, it is less than or equal to M, less than M. Suppose this K is not relatively prime to M, surely there will be a D that will divide K as well as M, right? Okay, see, this can be written like this. from this one. Suppose this k is not relatively prime to m, then d will divide both k and m. That d will divide k and m. So that d will divide this also, right? So this is a contradiction that this is equal to 1. So what we get is, if we find modulo m for these numbers, we get the reminders from this set only, but in some different orders. Let us see the proof now. The proof consists of two parts. First we will show that these two are prime to each other. Show that this is relatively prime to each other for each I. Then we will show that no two numbers Arj and Ari can be congruent modulo m if I is not equal to j. Okay. First we are going to show that Ari. First we are going to show that each of this number is relatively prime to m. Then only if you find the modulo to this number, we will get the remainder here. Right? First we are going to show that Ari is relatively prime to m. Suppose not relatively prime, then the GCD will be greater than 1. GCD will be greater than 1. Let P be a prime factor of this GCD. Prime factor of this one. So P divides this number as well as this number. P divides this one as well as this one. P divides Ari means P divides A or P divides Ri. P divides A or P divides Ri. Already we have P divides M. If we join these two statements, we get A and M are not relatively prime. Right? But in the statement it is given, in the lemma statement, the hypothesis A and M are relatively prime. So this is a contradiction. So P cannot divide A. Then if P divides Ri, combine these two, then we get Ri and M, they are not relatively prime. Ri and M, they are not relatively prime. Because P is the common divisor. Okay, they are not relatively prime. But this is also a contradiction. Why? Because R1, R2, etc. R phi of M, they are the least residues modulo M. Also they are relatively prime to M. So these are prime to M. So it has to be 1. The GCD has to be 1. So we have got contradiction in both the ways. So this cannot be greater than 1. This contradiction arises because of our assumption. So Ari is relatively prime to M. So we get is Ari is relatively prime to M. Now secondly we are going to show that Ari is not congruent to Arj mod M if I is not equal to j. That means this number as well as this number won't leave the same remainder when we divide by m. This number as well as this number will not leave the same remainder when we divide by m. Suppose these two leaves distinct reminders when we divide by m, we will get distinct numbers. So together there are phi of m numbers. There are phi of m numbers. If we find modulo m for these phi of m numbers, we will get phi of m distinct reminders. We are going to show this one only. Now, suppose this is not. Suppose this is not. Then Ari is congruent to Arj mod m for I is not equal to j. For I is not equal to j. Bring that one this side, we will get this line. But A and M are relatively prime. So we get M divides this one. M divides this one. But Ri, Rj's are the least residues. And they are less than M. They are less than M. And I is not equal to j means they can't even be 0. they are not 0 and this number is smaller than m. This is not equal to 0 and less than m and greater than 0. How m can divide this one? So m cannot divide this one, but m does not divide this one because of these conditions. So we got ARA is not congruent to this one. So from this one as well as from this one, this says that these two are relatively prime, and this says that this number and this number will leave different remainders when we divide by m. So with these two statements we conclude this paragraph. Thus the least residue of these numbers modulo m are distinct because of this one, and are in phi of m numbers because of this one. Also they are relatively prime to m. They are, if you find the modulo m to these numbers, they are relatively prime to m. Why? Because this one, okay, because of this one, okay, because of this one we get this is relatively prime to m, okay. So this phi of m numbers modulo m leaves phi of m numbers, and they are relatively prime to m and less than or equal to m. So they are a permutation of the least residues, this one, right? So those reminders, they are the permutation of the least residues of R1, R2, etc. R phi of m modulo m. In the next session, let us see proof of Euler's theorem. Thank you.